Similar to flash loans, there is a concept of flash minting that has similar concerns. Unlike flash loans, where the total amount of tokens that can be borrowed by a user is limited by the liquidity of tokens in that particular protocol, flash minting simply mints the new tokens that are handed to the user. And these again are only available within the context of a transaction, because at the end of the transaction, the flash minting mechanism will destroy all the tokens that were just minted and handed to the user. And similar to flash loans, if smart contracts that are working with such ERC20 tokens make assumptions about the balances of those tokens that are available for a user, then they could lead to overflows or other serious security vulnerabilities. And these again can be manipulated, and is a risk that needs to be kept aware of when dealing with external ERC20 tokens. So far, we have looked at different security aspects of ERC20 tokens. Let's now take a look at few other tokens that are nowhere as widely used as ERC20 tokens, but introduce some concepts that are interesting from a security perspective. One such token standard is ERC 1400. This token standard introduced the notion of permissioned addresses. And this standard was driven by Polymath and was related to the concept of what are known as security tokens. These are tokens that represent ownership in a financial security. And note that the security has nothing to do with the program or application security we are talking about. Such permissioned addresses could block transfers from certain addresses or to certain addresses. And this, as you can imagine, is interesting from a security perspective, because if those addresses are malicious or if they can be compromised, then it leads to a denial of service risk where transfers to and from such addresses can be blocked. So this is a risk that we need to keep in mind if our smart contract application ever has to deal with ERC 1400 tokens. As we said, these are not very often used or encountered, so we will not be getting into any more details and only talk about the surface level security implications that these token standards introduce. If you're interested in more details, I would encourage you to look at the token standards themselves. Related to the notion of permissioned addresses, ERC 1400 also introduced the concept of forced transfers, where there are trusted actors within the context of the standard that can perform unbounded transfers. So these trusted actors can transfer funds, arbitrary amount of funds, to whichever addresses that they choose. And this introduces a transfer risk that needs to be kept in mind when dealing with such tokens. A related token standard to 1400 is ERC 1644 that allows the concept of forced transfers that we just discussed. And this is again in the context of a controller role, which is a trusted actor in this standard that is allowed to perform arbitrary transfers of funds to arbitrary addresses. And this, as you can imagine, if malicious or compromised, can steal funds. So in this ERC standard, there is a risk from the controller address that needs to be kept in mind. ERC 621 token standard allows a different way to control the total supply of tokens. In this standard, there is a notion of trusted actors who can change the total supply after the contract is deployed. And this is allowed using the increase supply and decrease supply functions that are specified by the standard. And this introduces what is known as a token supply risk, where the token supply of such tokens can be changed arbitrarily after the contract is deployed. ERC 884 is another token standard that introduces yet another interesting security aspect. In this case, this token standard introduces the notion of cancelling and reissuing. And what this means is that the standard defines actors known as token implementers who can cancel addresses in the context of a contract that implements the standard. And in that process, what these implementers do is that they move any tokens owned or held by those addresses to a new address while cancelling the older address. And this, as you can imagine, from a user's perspective, introduces token holding risk, because if you are holding certain number of tokens in a particular address, then the token implementers could move those to a new address and cancel your existing address. ERC 884 also introduces the concept of whitelisting addresses, where a certain set of addresses may be whitelisted by a contract implementing the standard. Token transfers are allowed only to such whitelisted addresses and not to addresses that don't exist in this whitelist. This, again, as you can imagine, is a token transfer risk, because a user might want to transfer tokens to a particular address, but if that is not whitelisted, then that token transfer is not allowed. So with this, we have covered various security risks, pitfalls, and best practices specifically related to token standards. Most of them were related to ERC20 token standard, and a few of them were specific to these unique token standards that introduce very peculiar security aspects. Let's now talk about a critical concept of guarded launch. This framework of ideas is widely used by almost every project in the ecosystem today in some form or the other. And this was put together and made popular by the team at Electric Capital. The fundamental idea is that when a new project is being launched, then there could be failure modes, vulnerabilities that have not been considered or discovered. And because of that, it makes a lot of security sense for the project to launch with minimal risk and over time increase the exposure as and when the project team gains more confidence in the normal functioning of the system. And this idea is heavily inspired and motivated by a similar concept of what is known as canary development in the Web 2 world. However, the Web 3 world, because of notions of immutability, the difficulty of upgrading or updating code once it is deployed, and the immediate nature and the extent of exploit possible, these aspects make guarded launch in the Web 3 space somewhat different, perhaps difficult, but nevertheless more critical to implement and execute. There are multiple ways of doing guarded launches for smart contract applications. Let's take a look at the first such way of doing so. And this is by introducing the notion of asset limits. What this means is that during launch, the amount of assets that are managed by the smart contract application can be kept to a lower value than what is really possible or desirable. And over time, this asset value that is managed by the system can be increased gradually as we gain more confidence that this application does not have any further latent vulnerabilities that may get exploited and result in loss of these assets. And the rationale again is that at launch time there is likely a higher risk from latent bugs or failure modes that haven't been considered that could be exploited. So the best way to mitigate that is by introducing this notion of guarded launch, and in this case specifically with asset limits. Guarded launch can also be applied to asset types. Smart contract applications can deal with multiple asset types, for example, different types of ERC20 tokens, and each of these asset types may be associated with a different level of risk. So for example, there could be ERC20 tokens that are very widely used, well understood, time and battle tested, that are generally considered as safer to use. And there may also be newer or different ERC20 token types that have slightly different behavior than those that are widely understood, and those come with a much greater risk because of the lower understanding or the lower use. So from a guarded launch perspective, the idea is to launch with fewer asset types that are supported initially by the application, and over time increase this in a certain manner. And one way to do that is to first allow the use of known assets, or assets, like we said, are widely used or known and generally accepted as being safe by the community. And then later on, as the project matures, as the more confidence is gained, other asset types could be allowed within this application. So this again mitigates the risk in a guarded launch approach. Limiting the number of users that can use a newly launched application, new versions of the application or new features within that application, is a widely used and time-tested technique in the Web 2 world. The same concept applies to the Web 3 world, where upon guarded launch using user limits, a few trusted users are whitelisted or selected or chosen based on certain criteria, and only these users are allowed to use or interact with this application. And over time, as the project team gains more confidence that these interactions by the selected group of users is as expected or anticipated, they can open up the application to other users as well. The motivation, expectation, and the outcome with this guarded launch approach is similar to the other ones, where there is a higher risk initially, so limit it to a few trusted users and mitigate risk in that fashion. But then the idea is to gradually increase the exposure to other sets of users as well. Similar to user limits, we can also consider a guarded launch approach where there are usage limits. And what this means is that upon launch, the usage is limited across certain criteria, and then over time, these limitations are removed to allow more extensive usage. And this usage could be along the aspects of transaction size, the volume of the transactions, daily limits that are imposed on every user, or even rate limiting per user or across all the users of that application. So with these two guarded launch approaches of user limits and usage limits, it's easy to imagine how risk is mitigated, because if something were to go wrong, then only that limited set of users or limited set of transactions or the limited set of value of the tokens or any other asset held by that application is impacted. Composability is another aspect where we can apply the guarded launch approach. Recall that composability is a defining feature of Web3, where every application can expect to interact with or expect to be interacted with by any other application in this ecosystem. This makes considering these applications as Legos that can be picked and chosen in interesting ways, combined in very interesting ways to build applications that were originally unexpected. While this is a defining feature and even expected by design in the Web3 ecosystem, we have also talked about the security risks from unconstrained composability. Because applications can interact with, be composed with an arbitrary number and unknown applications, their differing assumptions, configurations, requirements, and expectations could lead to failure modes that have not been considered or validated in the context of this application. Therefore, composability becomes really critical from a guarded launch perspective. And one way to approach it is to again impose limits on composability, where upon launch, the application is only allowed to be composed or interact with known applications or protocol. And over time, extend this to arbitrary external smart contract applications that may pose an additional or increased risk. So this gradual increase of exposure from whitelisted or trusted contracts extending to arbitrary untrusted contracts is another guarded launch approach. Another guarded launch approach is to use the familiar concept of escrow from the traditional finance space. In this case, high-value transactions or high-value operations are escrowed, where there are time locks or specific governance capabilities that have the power to nullify or revert these transactions in case something unexpected happens with it. So the guarded launch approach is to first start off with an escrow capability, which upon greater confidence in the system is removed. The next guarded launch approach is what is known as circuit breaker, and this is perhaps the most widely used guarded launch approach by many of the smart contract applications that we see today. This is something that we discussed earlier, where smart contracts allow certain authorized users to pause certain functions or functionalities of that smart contract when there is an emergency. And upon recovering from that emergency, there are unpause capabilities for those functionalities, which again the authorized users can decide and trigger to recover from this emergency. This is something we discussed in the context of the OpenZeppelin pausable library that allows these capabilities to be applied selectively on different functions of a smart contract. So the guarded launch approach is to start off with this circuit breaker pause unpause capabilities and later renounce these capabilities so that those authorized users need not be trusted with pausing and unpausing, which if abused can lead to a denial of service attack on those applications. An extended or extreme version of the circuit breaker capability is what is known as emergency shutdown. In scenarios where simply pausing and unpausing the smart contract application does not help us recover from the issue at hand, and where there is something fundamentally broken or wrong with the smart contract application that needs to be fixed in a more involved manner, the emergency shutdown helps authorized users to shut or turn off the smart contract applications from allowing users to further interact with it. And it also allows users to reclaim their assets that are held by that application. And where possible, this capability could also allow one to reset and restart such smart contract applications. And from a guarded launch perspective, The idea is again to launch an application with this emergency shutdown capability, and over time, once we gain more confidence in the correct functioning of the system, remove this capability. And so far we have talked about removing these capabilities. The way that is typically enforced within smart contracts is to remove the authorized users who can trigger this capability, which can be done by making that list of authorized addresses an empty list or by setting them to 0 addresses. So this is yet another way or an extreme way to deal with emergencies with this guarded launch approach. So with this, we have discussed about 8 different approaches to guarded launch, which is widely recommended and used by the different smart contract applications today. So far, we have discussed security pitfalls and best practices focused on the Solidity language, the underlying EVM, the different token standards, and so on. For the remaining part of this module, we are going to up-level and discuss similar pitfalls and best practices, but focusing at the application level. These are software engineering best practices that have been developed and refined over decades and that apply specifically to smart contract applications as well. These application level aspects are arguably more important to discuss from a smart contract security auditing perspective because these aspects cannot be generalized across smart contract applications like we have done with Solidity or EVM level concepts. And because of that, there is a lack of tooling support for security pitfalls and best practices at this application level. And this brings about a greater dependency on manual analysis when it comes to security auditing. And when that is insufficient or incorrectly done, it has led to massive exploits that have resulted in losses of many millions of dollars. So with that context and motivation, let's talk about system specification. The design of any system or application starts with what is known as requirements gathering, where such requirements are determined based on the target application category, the target market, or the target users. And once those requirements are determined, they are translated or written or codified into a very detailed specification. And this specification is required to describe in great detail how the different components of the system need to behave to achieve the design requirements. And it's not just the how aspect, but also the why aspect. Why is something being designed and specified the way it is being done? And without such a detailed specification, a system implementation will not have a baseline to be evaluated against the requirements that we have collected earlier. And this is something critical for determining if the system behaves correctly, if the functions actually meet certain requirements that were desired and that were collected earlier. So to summarize, the design of a system begins with requirements, and these requirements are translated into a very detailed specification, which in future, once we have an implementation, allows us to evaluate if the implementation actually meets the requirements. System documentation, just like system specification, is another critical component from a software engineering best practice. And this is something that is often confused with specification. Recall that specification deals with design and requirements of the system, whereas documentation deals with the actual implementation itself. The documentation describes what the different system components do to achieve the specification goals and how they do that. This has to cover various aspects related to the assets managed by that system, the actors within the context of that system, and the various actions that these actors perform. It should also address the security specific aspects of the trust model and the threat model that are relevant to the system. So to summarize the design flow, we start with the requirements that helps us create the specification, which in turn helps us execute the implementation of that system. And this implementation should be accompanied by extensive documentation that helps one evaluate it against the specification for correctness across various attributes. So with that high-level view of system design, let's now start discussing security aspects related to various application logic related constructs and concepts. The first one is function parameters, and from a security perspective, one should ensure that proper input validation has been performed for all function parameters. And this is especially true if the visibility of such functions is public or external. Because in these cases, users who may potentially be untrusted can control the values that are assigned to these parameters. And such tainted values can affect the control and data flow of this function and any logic thereafter. So the best practice here is to make sure that there are valid sanity and threshold checks performed on these parameters depending on what types they are. So for example, if they are of the address type, then zero address validation should be performed, because otherwise they could lead to exceptions during runtime, or they could lead to tokens being burnt or access control being denied, as we have discussed in some of the earlier slides. The risk that we are trying to address here is from incorrect or invalid values being assigned to function parameters, either accidentally or maliciously by users interacting with these functions. The arguments that are passed to functions at the call sites and that correspond to the function parameters are also something that need to be evaluated from a security perspective. At a high level, the arguments that are used at the call sites, that's the callers, should match the parameters that are required by the functions or the callees. And this matching should happen both in terms of their validity as well as their order. Or in other words, the arguments at the call sites should be valid in that smart contract application's context to what the function parameters expect. And the order of such arguments should match the order of the function parameters as expected. So these are the best practices that need to be followed when it comes to function arguments and their corresponding function parameters. We have discussed function visibility several times, and this is something that is specific to Solidity language that has 4 visibility specifiers, and the order from maximum visibility to minimum visibility is as shown, which starts with public, external, internal, and then finally private. From a security perspective, to follow the principle of least privilege, it's critical to make sure that the strictest visibility is applied on the various functions. And the reason is that if a function is accidentally made external or public, when it should actually be internal or private because of some critical functionality that should not be exposed to external users, such a mistake can be exploited by users, some of whom may be untrusted, to invoke functionality that they are not supposed to have access to. This again is very relevant here because of the Byzantine threat model.